In this video, we're going to talk about multiplying and dividing rational expressions. So you've already simplified a rational expression, something like, if you see in example 1, just 4y squared minus 9 divided by 4y squared. You talked about how to simplify something like that, how you need to factor it, and how you can take any factor divided by itself and it becomes 1. But now what if it's multiplying to another rational expression, or dividing? So, to understand what you're allowed to do, I'm just going to show you a multiplying with numbers, 3 halves times 8 ninths. Now there's two strategies that you can take here. You can multiply the tops and make it 24 eighteenths, and then think about the largest common factors in 24 and 18, so that's going to be 6. So 24, so it's 6 times 4 and 6 times 3, and 6 divided by 6 is 1, so you just get 4/3. So that's one way you can do it. When you multiply fractions, you multiply the tops and you multiply the bottoms, and then you can reduce. Or what I can do is kind of think about how this is all one big numerator and one big denominator. So I could really think of it as 3 ninths times 8 halves and simplify it that way. Like 3 ninths is 1/3 and 8 halves is 4. So I get the same thing of 4/3. So like where the numbers are, as far as on the left fraction or the right fraction, doesn't really matter. So you can look at this and be like, okay, 3 ninths, that's 1/3. And 8 halves, that's just 4 over 1. And then multiply across, like 1 times 4 and 1 times 3. And get 4/3. So you're going to do the same thing with the rational expressions, where if something in the top left matches with the bottom right, you can reduce it. Or if something with the top left matches with the bottom left, you can reduce it. So it's like one big numerator over one big denominator, pretty much. Now I can't go ahead and simplify anything yet here, because my factors are 4y squared minus 9. I don't see 4y squared minus 9 anywhere else. I can't cancel out the 4y squareds because in the top 4y squared isn't a factor, it's a term. So the first thing I'm going to do is factor these two binomials. 2y minus 3 doesn't factor, but 4y squared minus 9 does. It becomes 2y minus 3, 2y plus 3, divided by 4y squared times 8y over 2y minus 3. So now I have a match of 2y minus 3 in the top left and in the bottom right, and that divides to 1. It doesn't matter that they're not directly on top of each other. Eventually they'll all get multiplied in the numerator and the denominator, and so those will reduce. The other thing I can reduce is this 8y over 4y squared. 8 over 4 is just 2. Y divided by y squared is just y. And now I take what I have left and multiply through the top. So what I have left is 2y plus 3 times 2. So 2 times 2y plus 3. Now in the denominator, all I have left is a y. So I could write it as 4y plus 6. I could distribute that 2 back in. You don't have to. Divided by y. And that's as far as that one goes. I can't cancel out the y's because the y in the top is a term, not a factor. You can only reduce factors down to 1. So in general, your steps are just, again, factor everything, reduce, and then multiply what's left. Multiply what is left. So in example 2, I have lots of trinomials. I have 4 trinomials, and they all need to get factored before I can see if I have any matching factors. I'm going to pause and do the factoring. If you have trouble factoring trinomials, please go back and watch previous videos or ask a question, look up how to factor. Okay, so now everything is factored. So now I'm going to see what matches I have. So Ooh, not much. Okay, well, this x plus 3 and this x plus 3 reduce. Oh, okay, this 2x minus 5 and that 2x minus 5 reduce. And there should have been a 2 here on the top right. So that's going to reduce with this 2. 2 divided by 2 is 1. And I'm left with quite a bit. So in the top, I'm left with 3x plus 1 times x plus 1. They didn't have any matches. And the bottom, x plus 3 times 3x minus 1. And you can leave your answer like that, or you can multiply it out. But that's all that reduced. So just make sure you factor correctly and then just see what matches you have. It's okay, like if this x plus 3, if they are from different fractions, because when you're multiplying, it's all one big numerator and one big denominator. So again, just factor, reduce out common factors, and multiply what's left. You can leave it in factored form still or multiply it out. Both are fine. But realize you can't break it down further. Knowing when to stop is actually pretty important with these. So let's move on to division. So what happens when you divide rational expressions? I'm going to show you just an example with numbers, so it kind of makes more sense. Now, when you divide, let's say you take the number 20 and you divide by a half. So it's asking, like, how many times does a half go into 20? Well, a half goes into the number 1 twice. It's going to go into the number 20 40 times. So in math, the way we do this operation is you multiply by the reciprocal, because 1/2 goes into 20 40 times. So it's the same as taking 20 and multiplying it by 2. Oh, I'm sorry. It does equal 40 because 20 times 2 is 40. So you change it to multiplication. So you're going to keep what's on the left, change to multiplication, and basically flip the fraction on the right. Keep, change, flip. Keep, change, flip. Keep the left, change to multiplication, and flip, or like use the reciprocal of what's on the right. So with division problems, the goal is just to change it into a multiplication problem. And then I can reduce 27 over 3 and get 9. And I can reduce 14 over 7 and get 2. And my answer is 2 times 9. That's what's left, or 18. So that's an example with numbers. So now let's do it with rational expressions. So I'm going to keep what's on the left. So I'm just going to rewrite that. Change to multiplication. And then flip what's on the right. So this flipped. That was my first step. So I changed it to multiplication. And then that fraction, I have it multiplying by the reciprocal. So now it becomes a multiplication problem like we practiced on the first slide, where I'm just going to factor everything and then see what factors cancel. So this one wasn't too bad to factor. I took out some GCFs, I had some trinomials, and let me look for matches. This is my favorite part. So I have x plus 1s, that's a match. I've got x plus 3s, the 2 and the 3, that doesn't reduce, so that's done. So now I'm just going to multiply what's left. 2 times x minus 1, x plus 2 times 3. Now this one's not too bad to multiply out, so I'm just going to go ahead and do that. 2x minus 2 over 3x plus 6. And that's the answer. So for division, you're going to change to multiplication. That's the goal. That's what you do with division. Now example 2 here has a little bit of both. So this just needs to flip. And if you ever see a combination of division and multiplication, the multiplication is going to stay the same. And it's just that division where you're going to keep what's to the left of it, change to multiplication, and flip that. So now the x minus 1's on the bottom, but this one on the right is going to stay the same. Now I'm going to factor everything and see what common factors I have throughout. All right, let's check. So I have x minus 1's, I have x plus 2's. Is that it? Yep, that's it. Okay, so there's a bunch left. So the top is going to be x plus 1, x minus 2, x minus 2. So I have x minus 2 twice. I can just write it as x minus 2 squared. And in the bottom, I have x minus 1. That would take a while to multiply it out, so I'm just going to leave it in factored form. That's fine. That's as much as I could reduce. It looked like I was going to have more, but nope. You might be thinking, hey, can I simplify this x plus 1 and this x minus 1? Well, no. We did see some tricks where if you had like negative x plus 1 over x minus 1, that does reduce because you can take out a negative from the top and it just becomes negative 1. But it needs to be the same numbers but complete opposite signs in order for you to do that trick. So if you have x plus 1, x minus 1, that's as good as it's going to get. All right, that's multiplying and dividing rational expressions.